Dear friends, today we are going to talk about a very important class of convex functions called the support functions of a convex set. In the last lecture we had studied convex functions which are expressed as maximum of a finite number of convex functions, irrespective of whether those functions are smooth or non-smooth. We studied those class of functions, studied the subdifferential, applied them to find KKT and all kinds of things. Here we are going to talk about max functions, special class of max functions, but we are not going to talk about max functions made out of finite number of convex functions, but an infinite family of convex functions. So we will talk about an index set T and a family of convex functions Ft, where the small t, which belongs to the capital T, is an index, where T could be an uncountably infinite set too, and could be a topological Hausdorff topological space, could be R in whatever, it's up to the situation. Now if we consider these Ft's to be convex and lower semi-continuous, then the function fx that you get is also convex and lower semi-continuous, which is a supremum of ftx. Of course we cannot write maximum here because we cannot guarantee that there will be a t for which we will have fx equal to ftx for each x. So this whole thing comes out of this simple fact that the epigraph of f can again be expressed as the intersection of epigraph of ft's, where t varies over the index set capital T. Now because f is convex, epigraph of t for each t is convex, so their intersection is convex because the intersection of arbitrary convex sets is convex. Similarly, epigraph of ft is closed because each of these ft is assumed to be lower semi-continuous. So intersection of arbitrarily closed sets is closed, so epigraph of f is closed, and hence f is lower semi-continuous. Of course it has to be proper only if the intersection of dome ft is not phi, because dome of f must be intersection of dome ft's, right? So here we are going to focus on some special type of max functions which are given by infinite number of the supremum of infinite number of convex functions. We are going to focus on those functions which are expressed as supremum of linear functions, or infinite family of linear functions. The most important of that, which you know, most popular rather, is the directional derivative of a convex function from Rn to R, and the directional derivative at x at any given direction h is expressed in this form, that it is the supremum of Vh, where V belongs to del fx. So here h is the argument of the linear function Vh. For every V, Vh is a linear function in H. So V is actually what defines the linear function, and it is acting as the T, the index, and this del of fx is acting as the index set. So for a fixed x, this is a function of H, and this is a convex function. But this is also a very special type of convex function called sublinear functions. So sublinear functions has the first property called subadditivity. So a function phi is subadditive because if phi of x1 plus x2 is less than equal to phi of x1 plus phi of x2. So here if we take h1 plus h2, then by simple idea about the supremum, that supremum of f plus g is supremum of f, supremum of f plus g is less than equal to supremum of f plus supremum of g, we come to this conclusion. Here I should write phi of del fx, which is missing, I am sorry for that. So this is called the subadditivity property, which is also, and there is another property called the positive homogeneity property, that phi of lambda x is lambda of phi x whenever lambda is greater than or equal to 0. This property is also satisfied by the directional derivative. Such functions which is both subadditive and positively homogeneous are called sublinear functions. So this is a special class of convex functions whose epigraphs are a cone, because here under a little convention that 0 into plus infinity is 0, we can always define phi 0 to be 0. So we can always write phi of 0. So a function phi from Rn to R in plus infinity is called sublinear if these two properties of subadditivity and positive homogeneity holds. Now what happens, I can always write phi of 0 is phi of lambda into 0 and lambda into phi 0 for any lambda greater than 0. So which means here phi 0 could be both plus infinity or 0 as a solution. But if I take lambda into 0 is always 0. When lambda into phi 0, even if phi 0 is infinity, I'll say lambda into plus infinity is 0. If I take that convention, that phi 0 will always become 0. So obviously, if it is a proper convex function, you can always have phi 0 is 0, right? So see, there are issues because some people define positive homogeneity only when lambda is strictly bigger than 0, but we make it little relaxed. So whenever this type of functions are proper sublinear functions, phi 0 is 0. So in our case, phi 0 is 0 in most of the situations. Any convex function which is positively homogeneous is always sublinear. So if it is positively homogeneous, we have to just prove that it is also subadditive, and this proof is deceptively simple. So you take 2x1 plus x2 from Rn and say f of half x1 plus x2 is equal to f of half of x1 plus f of half of x2 is less than equal to half of f of x1 plus half of f of x2. This is by convexity. But positive homogeneity shows that f of half of x1 plus x2 is half of f of x1 plus x2. This part. Now if I replaced this thing with this thing, then I get half of f of x1 plus x2 is less than equal to half of fx1 plus half of fx2, which gives me the subadditivity property, proving that it is sublinear. So here I have asked you to show that for a proper sublinear function, it will be a convex cone with a vertex at 0 and blah blah. So very important example is fx equal to mod x is a sublinear function. Fx equal to norm x in higher dimension is a sublinear function. If you have a function p which is sublinear and from Rn to R, then the directional derivative at 0 in any direction is actually obtained by just calculating the function value of p at that h. This is simple to show. Let us give you some other examples of sublinear functions to convince you that it's a rich class. We take the example fx equal to norm x with respect to q, where q is a positive definite matrix, symmetric positive definite matrix, of course. So it is given as root of x qx. So if q is identity matrix, which is also positive definite, then we get the normal Euclidean norm. Now, this particular norm, it is a norm, and in fact we'll show you at the end it's a norm. This particular norm is very useful in the interior point methods for convex programming. There's a book by Jim Rennegar called the mathematical, it's a mathematical approach to, it came out in SIAM, I'm forgetting the name, by James V. Rennegar, mathematical view of interior point methods for convex programming, where this kind of norms have been very, very, very strongly used actually. So you can easily prove that it is positive homogeneity, because when you put lambda x, lambda square comes out, and obviously lambda comes out, and you have lambda of fx. Now once you want to prove this, you start by proving, taking norm x plus q whole square and again writing from here the definition that norm x q square is nothing but this inner product. And then you come to this line, last but the second one. Now if you know how to prove Cauchy-Schwarz inequality, but you can easily show that this expression y inner product qx is less than equal to norm x with respect to q and norm y with respect to q, the q norm, and hence you get this expression. So hence the triangle inequality holds, and then it's subadditive. Of course you can say, okay, it was a norm, so you have already told it was a norm, it will be subadditive. But okay, it's a proof that the triangle inequality holds. Another simple example is a matrix function. If you consider Sn, the set of all n cross n symmetric matrices, then the maximum eigenvalue function of a symmetric matrix is a convex function from Sn to R. So this is the way we define the maximum eigenvalues. These are called Rayleigh quotients. You know some linear algebra where we are actually, the index set is nothing but the unit sphere. It's a unit sphere in Rn. Now for each x, once I fix x, as a function of a, it is linear. And hence this is a convex function, and once you can prove that it is positively homogeneous by the previous theorem, it is a sublinear function. So now we come to an important class of sublinear functions called support functions. So given a convex set C, the support function is a function from Rn to R union plus infinity, which is expressed as the supremum of the family of linear functions generated by the elements of C, where C is the index set, T, instead of T, C is now the index set and V is the index points. You can immediately understand if C was del of f some k, then the directional derivative at k in the direction h is a support function of the subdifferential set. Okay, it seems that it's going to rain outside. But you know, the support function, you cannot guarantee that it is a proper function. If C is compact, then it is finite everywhere. Otherwise, it is a convex function, it is a sublinear function, but you cannot guarantee that it is proper. It could be that for every x, this for every v in C, it blows up. Just blows up. So it could be just identically plus infinity. But in many cases, it is not. It holds good. Obviously, if C is compact like the subdifferential, you have directional derivative just the way it has for a finite valued convex function. The support function would be finite and nice and all those things. But it is lower semi-continuous. It's sublinear and lower semi-continuous. One important thing to know that if the convex set C is bounded also, right, then sigma C is finite, and if the sigma C is finite over the whole of Rn, then C must be bounded. Here is a proof, but I am not going to get into the proof details because here you might need to have some knowledge about functional analysis. But those who would know it and those who are possibly observing the proof, this is the proof given by Hiriarthy and is on the style of Hiriarthy and Le Marchal, following that famous book Fundamentals of Convex Analysis, which I can, if you want, I can show you. This is the book, but you may skip the proof, first thing, because it needs a little bit ideas of finding norms in functional analysis. So the idea is that if your set C is bounded, C could be open convex set, but C be bounded. If it is closed convex set, is compact, then phi Cx is finite for all x. But if phi Cx is finite, then it is the C must be bounded. So it's a very interesting characterization. The finiteness of the support function is linked to the boundedness of the set C, and it's so beautiful. It's such a boundedness and finiteness. Boundedness of a set C and finiteness of a function are linked, and that makes it's so powerful actually. Let us now compute a subdifferential support function. And this example is from Hiriarthy and Le Marchal. But Hiriarthy and Le Marchal has used a beautiful trick, linear algebraic trick, but it needs advanced knowledge about linear algebra. It needs advanced knowledge about positive definite matrices, that kind of square rooting a positive definite matrix, but we are not going to do it. They have a beautiful proof with linear algebra. We will simply use KKT conditions. It will be a different proof. The example is taken from there, but the proof is done through KKT condition. So I just worked it out while doing the notes. I thought maybe I give a different proof. So what do I mean? So given a set C, which is set of all S in Rn, such that SQS, it is not X, it is SQS, where Q is positive definite matrix, is less than 1. This is not an X, this is an S. SQS is less than 1. So which means norm of S with respect to Q square is less than equal to 1. It is called an elliptic norm because this set C defines a n-dimensional ellipsoid in Rn, right? Because if you write in terms of Q, it will be some Q1 square x1 square Q. So it will be canonical form of an ellipse, right? That what you know from standard analytic geometry. So instead of writing the max function, I write the mean function because we had been studying the mean function. So here I am minimizing a linear function over a convex set which is described by a quadratic constraint. Please understand that an ellipsoid, by its very definition of an ellipse, or ellipsoid means everything in the ellipse and the cover, the boundary and everything inside it. That's a compact set. So for every d, this is finite. So this thing has a solution. And because the ellipsoid has an interior, this problem, because this is a convex function, because SQS is a convex function if Q is positive semi-definite, so Q is positive definite here. So this is the convex function SQX minus 1 less than equal to 0, G1x. So this is a convex function. Now the Slater condition holds here because it has any ellipsoid will have an interior. So the Slater condition will hold. Now minimum of this, so there will be a minimizer. So minimum of this, if S star is the minimizer, is this. So maximum is nothing but minus mean of minus of SD, which is S star of D. So I have to just apply the KKT condition at S star, find the KKT condition S star and find S star of D. So because the Slater condition holds, so we can then apply the celebrated KKT conditions at S star. And first we take the gradient of this function, which is minus D, and then the gradient of this function SQS minus 1 is less than equal to 0. And that will give you 2 lambda QS star, because gradient of this function is 2QS, 2 lambda QS star equal to 0. And lambda of this thing is equal to 0. So this is called the complementary slackness condition. Now what happens is that when we are minimizing a linear function over a convex set, the minimum always occurs at the boundary. The minimum always occurs at the boundary. If we know that, then S star QS star must be equal to 1 at the boundary. And so lambda cannot be 0. We'll show that later on. And then we can make things much more easier. But even if we do not know this fact, that okay, for a linear function, the functional value has to be achieved at the boundary, we can still prove that S star QS star must be equal to 1 at the optima. S star is the optima, minimizer. Assume that it is strictly less than 1. If it is strictly less than 1, then this is negative. This one, S star QS star minus 1 is negative. To make this 0, lambda must be 0. Once you have lambda must be 0, you will have d equal to 0. Because we have started by taking d not equal to 0. Because if I take d equal to 0, there is nothing to prove. It is 0 anyway. So we are proving it for d not equal to 0. We are computing the value of sigma CD. So if I put, once I have lambda equal to 0, from this first equation 1, I will have d equal to 0. If I take this to be strictly less than 1, lambda would be 0 from this equation, and immediately it will give d equal to 0, which is a contradiction. So this must be equal to 1. So then I take the first equation and then multiply. I take d to the other side and then take inner product with respect to S star. And I know that this is equal to 1, so I get S star d equal to 2 lambda. And also, if I put lambda equal to 0, I'll again have d equal to 0. So lambda cannot be 0, so lambda has to be positive. Which means now I, again from the first equation, taking d to the other side and multiplying both sides by q inverse, because it's positive definite matrix, there's an inverse. So q inverse d is 2 lambda q inverse q S star. So q inverse q is I, identity. So q inverse d is 2 lambda S star. So S star is equal to 1 by 2 lambda q inverse d, because lambda is strictly greater than 0. So again, in the expression S star d from here, you put this expression of S star, that is 1 by 2 lambda q inverse d. So you get d q inverse d is 4 lambda square. So 2 lambda is root over d q inverse d. So S star d, which is the maximum, which is actually the value of the support function, is this. Because S star d is max of this is S star d, and that is nothing but the support function. So the support function is nothing but the norm of d in q inverse. So here what we are trying to show, that a sublinear functional, we have already shown that an elliptic norm is a sublinear functional. We are showing that the elliptic norm is the support function of an ellipsoid. So then how beautiful the name is so correctly chosen, the elliptic norm. Now if I take Q to be identity matrix, then using what we have just studied, putting Q equal to identity, we will know that the set C, which was the ellipsoid, will now become the closed unit ball in Rn, and its norm is nothing but the Euclidean norm. So norm is a support functional of the unit ball. So you are having a new view of the function norm itself. It's a support function. So any norm is actually a max function. You might say, I cannot write norm as a max function, is x1 square plus root over this. But here, a norm in n-dimensional space can be expressed as a max of a family of linear functions. This is so beautiful that it is a support function. So non-smoothness is linked with max functions. Max functions are everywhere in convex optimization. Here is so now you might suspect that possibly every sublinear function corresponds to some support function of a convex set. The answer is yes. If you take P to be a proper lower semi-continuous sublinear function, I have missed the line towards sublinear. It should be sublinear. Then P is the support function of a convex set given like this. Actually, this is nothing but a directional derivative. This is like that, nothing but the S is the subgradient, right? Subdifferential. We can look at 4-point in a simple way. Let us take a convex function. Then you see this directional derivative is a support function of the subdifferential. Now take any sublinear function of finite valued. Then P of H is P dash of OH, we already know, which, as you know from this fact of convex function about sublinear, is max of V of del P0 VH. So for P of H, the functional value of the sublinear function at any point is nothing but the support function of the set del P0 at H. So every P, so every sublinear functional is a support function of the subdifferential of P at 0. That is why we didn't bother about other points of the sublinear functional, the subdifferential at other point. We just bothered about del P0 because this is the role del P0 is playing. It is telling you, give me any sublinear functional, del P0 is the set. For any finite sublinear functional, del P0, the subdifferential of P at 0, is the set, compact set C, whose support function is P. That is, there is a link between, there is a one-to-one correspondence between a sublinear, finite valued sublinear function and a convex compact set. And here is this link. Now let us look at some important properties of support functions. Now we will be now talking only about closed sets. Let A and B be two closed sets and A is a subset of B. Then the support function of A is always less than the support function of B. Now if you scale as convex set A by alpha, where alpha is strictly greater than 0, it is same as scaling the support function itself by the number alpha. Okay. Here comes the next proof. So if you have two sets A and B, then if you make the Minkowski addition, that is, take V from A and W from B, and V plus W is an element of A plus B, the Minkowski addition that we talked in the very first lecture, then we can prove that the support function of the closure of A plus B is sum of the support function of A plus support function of B. You see, if you add two closed convex sets, they do not give me a closed convex set. They give me a convex set, but they do not give me a closed convex set. The reason is that there is some issue with the taking of the limits. There are simple examples, we will not get into that. But if one of the sets, A or B, is compact, then A plus B is also closed. So to prove this fact, you have to rely on a very simple fact that you give me any convex set A, maybe closed, may not be closed, I don't know, suppose it is not closed, then the support function of the closure is the support function of the set itself. Once you do this, you can, I have a proof here, a very simple proof, that because A is always contained in A closure, so what we learnt in the property 1 is that sigma A is less than or equal to sigma A closure. In fact, you don't have to take closed sets A and B to prove sigma is less than or equal to sigma B. In fact, for any set A and B, the supremum over a larger set is always larger. Just that's the idea. I have written closed set just because we are discussing everything about closed sets. Now, suppose I have S in A closure. Then there must be a sequence Sn in A which converges to S. That is the meaning of an element being in a closure. Now, so S of D is limit of Sn of D. Now, sigma A of D is greater than or equal to Sn D for any D. Sn is an element of A, this is by definition, because sigma A D is the max of all the S in A. So, sigma A D, because this side doesn't depend on the N, is greater than the limit of Sn D, which is equal to SD. Now, this side is independent of the S, sigma A D is a number now, it's just a number. So, this is true for any S you take in A closure. We started with some S. So, you can always argue and come to this point. And so, what you did was just you then took the supremum here over A closure and you got the opposite equation from what you have got here. So, taking these two equations, I have equality. And then of course you can prove that once I know that this is equal to this, and then it is a very easy thing to prove it. Because here S1 belongs to a different set and S2 belongs to a different set, then the supremum is not less than equal to but equal to. So if F is over X1 and G is over X2, then sup over X1 plus X1 in A and X2 of B is sup of F over X1 plus sup of G over X2. That's the sup of F plus F of X1 plus G of X1 over X1 X2 is equal to sup of F of X1 plus sup of F of G X2. This is a standard result. So we are back to square one. So what would we do with this infinite family of a convex function which may not be linear functionals, right? We have shown norms are actually support functionals. They are that is the beautiful thing that we learned here, that they are actually expressed as the max of infinite family of linear functions. While mod of x is a maximum of two linear functions, x and minus x, when you are in R. But once you get in R2, once you get in Rn and all, it's infinite family of linear functions. Now there is a class of problems where these kind of functions, family of convex functions, become important. This is called the semi-infinite problems, where I minimize a convex function over inequality constraints gtx less than equal to 0, but the index set, this t, the index is not finite. It is not I is from 1 to m. It is that for all t varying over some capital T, the index set. But these kinds of things comes up in environmental science when designing environmental policies, in economics, in approximation theory, many other things. There's a very good book which I'm going to show you, written by two very good researchers in optimization and my friends also from Spain, Linear Semi-Infinite Optimization, published by Wiley in 98 by M.A. Goberna, Miguel Angel Goberna and Marco A. Lopez. So this is a wonderful book which gives you beautiful applications why this class of problem is important, and it has a lot of applications in statistics. So what can I do is that I can write this as that the convex semi-infinite program can be written as minimize fx subject to gx less than equal to 0, where gx is supremum of gtx. So if you want to write some basic optimality conditions, you must know the how to compute the subdifferential of x. And that is what we learned to compute. And this is a result from Hiria Turuti and Le Marchal. But here we are writing it in a slightly different way, not exactly taking what they have done. So consider a function fx is equal to max t element of t f tx. This is now a very common result. I can put many books as a reference to this. So I'm just telling that okay, Hiriartu and Le-Marchal is my personal favorite, so I would like to talk about this. Also, you can talk about Ruzinski's book on nonlinear optimization. Also does this. So if T is a compact set and the map T to ftx is either continuous or upper semi-continuous, because if as a function of T for every x, ftx is upper semi-continuous, for given an x, if ftx is upper semi-continuous, then if you maximize over T, it will be finite. And then the maximum would be achieved. So there will be a T for which fx is ftx. So then f is finite value for each x, and del fx is written like this. But jx is the set of all indexes for which ftx equal to x. Now this is not finite, this could be infinite. Now you may ask, what is the meaning of convex hollow with union of infinite sets? There is no definition of convex combination of infinite points. Then you have to talk about kind of strange kind of lambda i's where infinite sum is 1. No. You just take finite number of elements from them and make a convex combination. Keep on doing for all possible finite number of all possible convex combination. Given a set S, what is the meaning of convex combination? Taking any number x1, x2, xm from the set and making a convex combination. M could be 1, M could be 2, M could be 3, M could be 4, as large as you want. So that is the meaning of convex combination. So when you choose a convex, an element, there are always only finite number of points whose convex combination you are taking. So I will leave you at this. I think this is quite heavy metal today, and in the next class, next week we are going to start actually algorithms. What is the meaning of descent in non-smooth convex optimization, and we are going to talk about the subgradient methods. So here are my references today. My favorite Hiriartu and Le-Marchal, also the book of my friends. By the way, I do not know Le-Marchal, but I know John Baptist Hiriartu very well. Superb mathematician, beautiful writing. I've always enjoyed his writing and papers. I think anybody in convex optimization should look into this book, because you will learn a lot. Because convexity has so many hidden treasures, and you do not know what would be needed while you are trying to analyze an algorithm. Algorithm in convex optimization is not just a science. It is a science, of course. It is not just mathematical derivations. It is a pure form of art too, and that you have to keep in mind. So with this, I want to tell you a good night, and thank you very much.